This is lesson 23 in our Calculus 1 series, sigma notation. Sigma notation is used to conveniently denote a summation. So for example, if we want to sum up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, we could write this using the Greek letter sigma. We'll put an I equals 1 on the bottom, a 7 up on top, and an I inside the summation. I is called the counting index. It starts at 1 here, and it goes up by 1 until we reach 7. And the value that we are summing up is I itself. So when I is equal to 1, we have our first term here, and we need to put in I. So we put in 1. When I is equal to 2, this is our second term, and again, we need to put in I. So we put in this time a 2. And similarly for the rest. And so this is how we would represent this summation using sigma notation. Notice that we could also represent the same sum starting our index at 0. Then notice when I is equal to 0, what number do we put into our sum? We put I plus 1. When I is equal to 1, again we need I plus 1. So for this summation, with I starting at 0, it goes to 6, and inside the summation is I plus 1. So this is another way to represent the same sum. It's just using different indexing. Let's take a look at this example. Here we have 2 plus 4 plus 6 plus 8 plus 10. And we can represent that with I going from 1 to 5, as the summation of 2i. Because notice when I is equal to 1, when we have our first term, the number we need in our summation is 2. When I is equal to 2, we have our second term, the number we need is 4. When I is equal to 3, the number we need is 6. So in each case, we're taking 2 times I and putting that in our summation. And so one way we can represent this sum is with I going from 1 to 5, the summation of 2i. Now notice this sum is the same as the one we have here with a 2 factored out. If we factor out a 2, inside the parentheses we have 1 plus 2 plus 3 plus 4 plus 5. And we can write this as 2 times the summation, I going from 1 to 5, the summation of I. And notice these two are the same. And so it's always going to be that you can take your constant multiple outside the summation. Let's take a look at this example. Now we are going in the other direction. We are given the summation and we're asked to evaluate it. So what is the value of this summation? Well, I starts at 0 and goes to 4. So when I is equal to 0, we want 2 times 0 minus 1. 2 times 0 minus 1. Then I is going to increase by 1. I is going to be 1, so we're going to have 2 times 1 minus 1. Then when I is equal to 2, we're going to have 2 times 2 minus 1. Then 2 times 3 minus 1, and 2 times 4 minus 1. I stops here at 4. And so evaluating this, we have a negative 1, plus 1, plus 3, plus 5, plus 7. And that gives us 15. And so the value of this summation is 15. Let's take a look at another. Here we have I going from 3 to 7, the summation of I squared plus I. So we start with I equals 3, and we're going to have a 3 squared plus 3. Then I increases to 4, and we're going to have 4 squared plus 4. Then plus 5 squared plus 5, plus 6 squared plus 6, plus 7 squared plus 7. And we stop there. That is the upper bound for I. And evaluating here, we have 9 plus 3, that's 12. 16 plus 4, that's 20. 25 plus 5, that's 30. 36 plus 6, that's 42. And 49 plus 7, that's 56, and adding that up, we get 160. Let's take a look at another. Write in summation notation. So we're given radical 3 plus radical 4 plus radical 5 plus radical 6 plus radical 7, and we're asked to write this in summation notation. Now, the easiest thing to do would be to let I equals 3 here, and this way it goes up to 4, to 5, to 6, to 7, and so I goes from 3 to 7. And what's inside our summation? It's radical I. And so this is the simplest way to write the summation. But note, there are many ways that we can write this. If we wanted to start our indexing at 0 and have I equals 0, I equals 1, I equals 2, I equals 3, I equals 4, we could have I going from 0 to 4. And then if I is equal to 0 here, we need 0 plus 3 inside the radical. Here I is equal to 1, we need 1 plus 3. So in each case, we need radical I plus 3. And so that's another way to write this summation using sigma notation. But notice there are infinitely many ways that we can do this, and so keep in mind that summation notation is not unique. Let's see how we can write this sum in summation notation. We have 1 plus 4 plus 9 plus 16 plus 25 plus 36. So I notice here that we have squares. We have perfect squares here. So this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So I think the easiest way to write it would be to let the index I go from 1 to 6. And then inside the summation we have I squared. And that would be the simplest way to express this in sigma notation. Let's take a look at the next one. We have x plus x squared plus x third plus dot 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 plus x to the nth power. So notice here we have an x to the first power, x to the second, x to the third. So again, it looks convenient to start I at 1. This would be I equals 1, I equals 2, I equals 3, all the way down to I equals n. And so we would have the summation, I starts at 1, goes up to n, and what is inside our sum? It's x to the ith power. Let's take a look now at some useful summation formulas. Here we have the summation I going from 1 to n of a constant c. And this is equal to c times n, because what we have is c plus c plus c plus c plus c n times. So this is equal to cn. For example, if we have the summation I going from 1 to 4 of the number 5, this is 5 plus 5 plus 5 plus 5. We have I equals 1, I equals 2, I equals 3, I equals 4. It doesn't matter what I equals, the number inside the summation is always 5. So we have 4 copies of 5 here, so we have 5 times 4, which is equal to 20. So this is c times n in this case. Now if we have I going from 1 to n of I, this is going to be n times n plus 1 over 2. So for example, if we needed to sum up I going from 1 to 25, the summation of I, this fits exactly into the formula with n equals 25. So our summation would be 25 multiplied by 26 over 2. And so in this case, this is 325. So this is a nice convenient formula for summing up I. It's especially handy when the upper bound on I is large. We also have a formula for I going from 1 to n of I squared. That's n times n plus 1 times 2n plus 1 over 6. And so, for example, in this case, if we have I going from 1 to 10, summation of I squared, n is equal to 10. And so we're going to have 10 times 11 times 21 over 6. And in this case, that simplifies to 385. Again, it's a nice convenient summation formula. We also have one for I to the third, I going from 1 to n. This is n squared times n plus 1 squared over 4. So for example, I going from 1 to 20 of I to the third it's going to be 20 squared times 21 squared over 4. And so in this case, that's 44,100. And using the formula is much nicer than actually writing down 20 terms and adding those up. Let's take a look at what we have here. This summation is going from I equals 4 to 20 of I to the third. But notice the formula says I has to start at 1, going from 1 to n. So the only way that we can use this formula is if we write this summation in terms of other summations starting at 1. So in other words, we need to write this as a summation from 1 to 20 minus a summation from 1 to 3. And this way we can use the formula here with n is equal to 20. We can use the formula here with n is equal to 3, and then we can subtract. So we made this computation, I going from 1 to 20 of I to the third. We made that up here, that's 44,100. And here, I going from 1 to 3, again, it's n squared times n plus 1 square. So here, n is equal to 3. This is 3 squared times 4 square over 4. And so simplifying, we have 44,064. But again, just remember that to use these formulas, the summation needs to start at I equals 1. So sometimes we need to rewrite our summations in terms of summations that start with I equals 1. Let's take a look at the next example. We have the summation I going from 1 to n of 3 plus 2i quantity squared. Now, especially because we don't have a number here, we have an n, we know that we want a solution in terms of n. And so we know we want to use those formulas, and so we're going to square this out first. So this is 9 plus 12i plus 4i squared inside the summation. And in order to use the formulas, we want to break this into 3 summations. This is summation of 9 plus summation of 12i plus summation of 4i squared. And we saw earlier that constant multiples can be pulled outside the summation. So we can pull this 12 outside the summation, that'll go here. And we can pull this 4 outside the summation, that'll go here. Now, what we have perfectly fits the formulas. We have I going from 1 to n of a constant. In the formula that was c, and we know that's going to be c times n. So here we have 9n. Here we have I going from 1 to n of I. We know that that's going to be n times n plus 1 over 2, and the constant of 12 just multiplies that. Here we have the 4 multiplied by, and this formula is n times n plus 1 times 2n plus 1 over 6. And so now we just want to simplify here a little bit, and we have 9n plus 6n times n plus 1 plus 2/3 n times n plus 1 times 2n plus 1. And we could leave it there, or we could expand and simplify further. Either way is fine. Let's take a look at another example. Notice here our index is not written as I, it's written as k. That really doesn't matter, it works the same way. Here k is going from 0 to 8, cosine of k pi. So this is cosine of 0 pi plus cosine of 1 pi plus cosine of 2 pi all the way up to cosine of 8 pi. And so we need to make all of these trig evaluations, and to do that I like to look at my sketch of the cosine curve. It helps me make my evaluations. Cosine of 0 is equal to 1. That's here. Cosine of 1 pi is negative 1. Cosine of 2 pi is positive 1. Cosine of 3 pi is going to be back here again at negative 1. And so we're just going to be alternating here between positive and negative 1s. And so adding these terms up, we get a positive 1. Let's take a look at another example. The summation k goes from 3 to 8, sine of k pi over 2. Please pause the video and work on this. Here we have k starting at 3, so our first term is sine of 3 pi over 2. And then k is increasing by 1, so we have sine of 4 pi over 2 plus sine of 5 pi over 2, all the way up to sine of 8 pi over 2, since our maximum value for k is 8. And so evaluating here, we have sine of 3 pi over 2, which is negative 1. Sine of 2 pi is equal to 0. Sine of 5 pi over 2 is positive 1. It's the same as sine of pi over 2. Sine of 3 pi is equal to 0. Sine of 7 pi over 2 is equal to negative 1. And sine of 4 pi is equal to 0. So totaling this up, we get a negative 1. Now we'll be using the summation notation in the next few lessons. And this concludes our lesson on sigma notation.